All right, now we're going to skip 17.7. It's all about aspirin. If you're curious about it, you can read it in your book, but I'm really not going to talk too much about it in these slides. So 7.8 now is going to talk about esters and amides. How do you form esters and amides? And amides we're going to talk quite a bit about when we get to the amino acid chapter. All right. So basically what you do is what's called an acyl substitution reaction. All right, you have a group here, either an OH or an OR or an NR2, and you add some sort of HY to it. Okay, and basically what happens is this Y substitutes the X. Okay, so these two switch places, so Y ends up on the acyl group, you can see right here, and the H pairs up with the X. All right, so we're going to see a few of these reactions. Okay, here's probably the most easiest of them all. This is the esterification, all right, because we're forming an ester. So you take a carboxylic acid plus an alcohol in the presence of acid, all right? And what you can do is you can put on that group. So basically what happens is this is your water. Notice water pops out, and then your OR group replaces the OH group, and you formed an ester. All right, it's what's actually called a Fischer esterification. That's the name of the scientist that came up with it. We've also talked about Fischer projections when we talked about the stereochemistry chapter. And so here's an example where you can take a carboxylic acid and an alcohol, methanol, and make an ester out of it. Okay, by doing a Fischer esterification. So this is just one of the reactions that you have to write down on your card. All right. Here's another one. This is also what's called an equilibrium process. What's an equilibrium? That means that the reaction is reversible. That means as soon as you form products, the products can then, in the presence of acid, re-break back down to the carboxylic and the alcohol. However, we take advantage of something called Le Chatelier's principle. Now, you might have learned this in Chem 101. Okay, but what Le Chatelier's principle is that you can drive an equilibrium towards one side of the reaction by changing a reagent. Okay, so what does this mean? I'm in an equilibrium. Okay, if I want to form the product, let's say I want to form a lot of the product, what you do is you increase the concentration of these two, or just one of them. So like the methanol is pretty cheap. So if I increase this concentration, so instead of a 1-to-1, like if I have 1 mole of this and 1 mole of that, what I would do is 1 mole of this and like 1,000 moles of this. So I would do a huge amount of this. So what it does is it drives the equilibrium that way based on Le Chatelier's principle, and you can form more of the product. Okay, so you can use excess alcohol, as I said. Another one is if you take another reagent like water, and I decrease it. So as I'm doing this reaction, if I remove the water, the equilibrium tries to replace the that water. Since I don't have water, so in order to go this way, in order to go from my products to the reactants, I need water. Well, if I remove the water out of the equation, then this just keeps going and forms my product. I don't have water to reform the starting material. Okay, so again, you can either increase a reagent or decrease a reagent. If you increase it, it's going to drive it the other direction. If you decrease it, it keeps going that way. So what I would do is I would add a lot of methanol, and then I'd put in some sort of a drying agent and remove the water so that the equilibrium will be driven that way. Okay, if you've never learned the Le Chatelier's principle, or if that was a little confusing, we can talk more about it in class. Please ask me in class. All right, another reaction is to form amides. Same way, so instead of an ester, so an ester was a carboxylic acid and an alcohol, an amide is a carboxylic acid and an amine. Remember, this is an amine. And particularly, you need either a primary or a secondary amine. Okay, what that means is you need at least one hydrogen, or one of these R groups could be a second hydrogen. Okay, you have to have at least one R group or 2 R groups, but you can't have 3. You have to have at least a hydrogen. And the same thing, you're going to form a water molecule. Notice water, and then the remaining compound goes on your acyl group, and that's how you form amides. Okay, so here's an example. Take acetic acid plus ammonia and form the amide. All right. So here, first of all, here's an example of ammonia. This is just ammonia. This is an example with methylamine. You also have to heat the reaction. I forgot to say that. That triangle means heating. Okay, so you can take methylamine and form a secondary amide or a tertiary amide by using a secondary amine. Okay, this next part is kind of the reverse of what we just talked about, and this is the hydrolysis. So we've kind of already talked about the hydrolysis. Let me go back up here. When we talked about the Le Chatelier's principle, we said that this is reversible. Okay, well, if I want to imagine I have an ester and I want to go the other direction, I want to form the carboxylic acid. Well, add water and acid to it. And based on Le Chatelier's principle, if you increase this now and decrease the alcohol, you can drive the equilibrium the other way. That's exactly what we're doing here. This is hydrolysis. We're starting with an ester this time, adding water, and you can actually cleave this off and put the OH in place of it. So notice you're forming the alcohol here. That's one of your products. And then the OH is attaching to the acyl group, and you're hydrolyzing to the carboxylic acid. So it's the reverse of the Fischer esterification. All right, so here is a real example. Taking water, cleaving off the ethyl part of it, of the propanoate, to form ethanol and propanoic acid. The equilibrium is driven by the right by using a very large amount of this. You drastically increase the amount of water in there. Okay, and you also have to add an acid as catalyst. Notice we have the sulfuric acid as our catalyst. Okay, so an example of an ester hydrolysis using aqueous base is called saponification. The reason is because, notice, isn't this kind of like what we said soap was kind of like? You have this very polarized head with a very non-polar part of it. So they call it saponification, even though technically this is not a soap, but it's the same type of reaction. You take, in this case, you're using sodium hydroxide rather than acid. Same thing. So notice in this case, water and acid hydrolyzes. So that's called hydrolysis, but saponification is when you use a base instead and you form an O-. Okay, so this base hydrolysis forms the carboxylate ion rather than the carboxylic acid product. Okay, you can also do hydrolysis of amide, same thing. In the presence of acid, all right, and water, you can cleave this to form the carboxylic acid and the amine, and usually it's a quaternary amine, all right, or the amine salt. All right, so here are some examples. Again, taking the amide plus sodium hydroxide, you can hydrolyze it off to form the carboxylate and ammonia. That's in base. You can do an acid or in base. Okay, so just to kind of give you some real life examples, triglycerides, or triacylglycerols, also known as triglycerides. All right, they're commonly naturally occurring esters. Yeah, they're called triglycerides. They have 3 ester groups. Okay, so a triglyceride is basically this group, but you have these big, long, fatty tails. That's why triglycerides are considered fat, because they're these long, fatty tails. Okay, they are lipids. This is what lipids are. Okay, they're water insoluble in the presence of fats and oils. Okay, animals store in energy. Again, triglycerides. They're calling them triacylglycerols, but they're really called triglycerides. All right, you can use an enzyme called lipases that will hydrolyze off these triglycerides. Okay, diets high in fat lead to obesity, so the fake fat, Olestra, was invented in order to replace some of these triglycerides in snack foods. I don't know if you've ever heard of Olestra. I think they show a structure of it. But it's basically this big, gigantic fat molecule that our bodies can't break down, and I think they put them in potato chips and Ruffles in particular. I don't think they use it anymore because it had a pretty nasty side effect. What basically happened is the fat just kind of ran right through you and caused some issues. Just imagine big fat molecules running right through you very quickly. All right, so the lipase enzyme cannot hydrolyze the Olestra, so it passes through the body, providing no calories to the consumer. So you still have the fat, but it had no calories, but you had to run to the bathroom quite a bit. Sorry for the visual, but that's kind of why it's not used anymore. But pretty much lipase, okay, an enzyme, breaks these bonds right here, and you form, these are what's called fatty acids. Okay, why are they called fatty acids? Because your R groups are 12 to 20 carbons long. So it's the fat part, it's the hydrophobic part, and it's an acid because it's a carboxylic acid. So these are called fatty acids. That would be the other name for these once you hydrolyzed off the ester groups. Okay, so here's the structure of Olestra. What they basically did is they took a sugar molecule. Notice this molecule right here is sucrose. And then they put these gigantic long R tails all along this sugar molecule. Okay, here's kind of the structure of it. So you can see this is a gigantic fat globule. Okay, and they use this as a fat replacement in foods rather than trans fats or any of those fats. But it did have a really weird taste. And like I said, your bodies couldn't really break it down, and our bodies really had issues with it. Okay, so we're going to stop right there, and when we come back, we will talk about esters and what kind of compounds esters make.